section 1.2, and this is about the functions. I'm going to write the definition first and then we'll talk about that. A function is a relation from a set X into a set Y such that every X in X has exactly one Y in Y. The set X is called domain, and we'll talk about domain in a moment. And the set Y is called codomain, or in simplicity we'll call it range. Well, I have told you guys, if you want to be a good student, you should be good at the definitions. If you know the terminologies very well, you will understand very well. For example, just imagine you are a physician and you don't know the terminologies they use. So all the languages, they have terminologies. Similarly, mathematics, it has terminologies. The notion of function is extremely important. And we will see it everywhere throughout this course. Even when you go to college or university, you are going to see it everywhere. So make sure you understand it. When we say a function, it says a function is a relation. Anybody know what a relation is? Okay, if you don't know what a relation is, most probably you know what a function is, because every relation is not a function. If every function is a relation. Okay, so when we say a relation in general, so for example, if I say that A is related with B, and this R means that is a brother. So A or B, it will mean that A is a brother of B. So you get some idea about the relation, right? When we are dealing with numbers, if we say that A is R related with B, where R, it means that is less than. So it means that A or B, or A is related to B, it means that A is less than B. It could be A is equal to B, or it could be less than B, greater than B, less than or equal to B. All of these are relations. So when we say what a relation is, we see the definition. It says that a subset of Cartesian product is called a relation. So someone says that, well, I want to understand a function. The definition says function is a relation. And you say that, well, I don't know what a relation is. So you see the definition of a relation, and it says that any subset of a Cartesian product is a relation. What about if you don't know what a Cartesian product is? Can you understand relation? So you say that, what is a Cartesian product? Okay. So we go to the next definition, which says that Cartesian product so assume that we have two sets A and B. So the Cartesian product between A and B is the collection of order pairs AB such that the first element belongs to the first set and the second element belongs to second set. Well, we got some idea about the Cartesian product, but we see that it seems like this is the product of sets. The next question is, do we know what a set is? Anybody know the definition of a set? Nobody? You don't like sets? You guys drink tea? You guys eat dinner? Are you familiar with the dinner set? Yes? No? Never heard? You don't know what dinner set is? What about tea set? Are you familiar with tea set? Do you know water set? So what what is water set? Anybody know? You guys don't drink water? So what comes to your mind when we say water set? So what is included in water set? What is the stuff related to water? How do you drink water? There should be some glass and a bigger pot where you put some water. It's a pitcher. Do you need anything else for that? It's like you need a pitcher but if I say that there is one glass and one pitcher, can you say that this is a water set? Okay, so there are some well-defined rules which we say that, okay, if we have 6 glasses and one pitcher, we can call this one as a water set. Okay. Similarly, when you say tea set, what do you need for a tea? Teacups. What else? Teapots. What else? Okay, yes. What else? Yeah, teapot, yes. Sorry to say. Tea plates, okay. Teacups, tea plates. Yeah, sugar, creamer, it's like something which you put milk in it. So when you make all this collection, you call it a tea set. Similarly, dinner sets, they have different levels. There could be some with 6 plates, maybe some with 12 plates, some, it's like it depends how big. So they are related with the dinner. But the question is, why do we call them a set? Okay, so one thing you note that when we say a set, we are talking about some collection, right? Now the question is that what we are trying to collect. Now that's a demanding question, what we are trying to collect. So if we are trying to collect some stuff which is related with the tea, we call them tea set. If it is related with the dinner, we call it dinner set. If it is related with water, we say water set, and so on. So we say that we are doing a collection of objects. This is the simplest definition of a set. We are collecting. Collecting what? Objects. Some books they call things. That's what we learned when I was your age. The definition was the collection of things. When we say a thing, does it mean anything? That's the question. Okay. So, for example, I say that there is a set S which contains 1, 2, 3, alpha, and Casper. You know what 1 is? Do you feel any doubt when you say 1? 2? Do you have any doubts in your mind? 3? Alpha? Are you guys familiar with alpha? Casper? Do you know who Casper is? What is that? It's a cartoon. It's a cartoon of what? It's a friendly ghost. Okay? Well, the question is that when you say ghost, oh. So the first question is it real? Do we know? Have we seen it? Okay, so there are some doubts, some questions. When we say a set is a collection of objects, we make sure that every element is distinct. Don't have any doubts. That should be the part of the set. Okay, we will not make any collection. Anything into the set which makes some things doubt, which are like illusions. Can you make one example? One more example like that, where you see that the things are not clear, like Casper. Give you guys 10 seconds. Think about that. And I'm going to ask one by one. Just one thing which we cannot add to a set. Anything which comes to your mind. You know, just like it's not likely. You don't need to worry about it. Okay, what do you think? Oh, they are fine. They are numbers. So there is no illusion in that. We know that those numbers are maybe kind of, but those are numbers. We are fine with that. We are fine with that. So, no idea. That's fine. You have no idea. So everything is clear in your life. I mean, there is no illusion.
My example would have been ghost, but we did that.
Ghost, okay. What is that? What is that? Okay, yeah, that's acceptable. No idea, that's fine. Aliens, okay, that's acceptable. Okay. Say again? Vampires? Okay. Yeah. Okay, you are going in one direction. Yes. Okay. Okay, well, that's the same direction. Well, that's fine. You know, for example, I say my feelings. Okay, so the question, everybody have feelings. But can we make a set of feelings and then we can just play with them? That's a difficult question. Similarly, you say, for example, my dreams. Okay, so many of us, we have dreams. We think about that. And we know that, well, we can talk about that. But can we make a collection of dreams? That's a difficult thing, okay? So when we say a set, we make sure that everything, whatever is part of the set, the elements of the set, they should be very crystal clear. That's why we use the term distinct. They have to be distinct. Okay? And some example could be just like we say angels. Okay. Okay. The second thing is assume that I say S is the collection of I take this parenthesis of I say that the collection of pretty girls. Assume that, or handsome boys. Okay, think about that. Are you okay with that? Do you think this set is valid? It's legal? What do you think? It's fine. It's not fine. Why not? Okay. Okay. Yes. Yes. Next. What do you think? Is this set okay, legal? Okay. Well, once again, the question is that, are we clear about how to define beauty? That's the question. And do we have a definition of beauty? So we have a problem here as well. We don't have a clear picture. Maybe someone asks your mom and she thinks my kids are the most beautiful in the world. Okay, but what about the other people? What do you think about that? So when we have some opinion, anything which is clear, okay, it has to be clear to everybody. So we have a problem with the definition. Similarly, we say that the collection of, for example, smart people, or collection of stupids, something like this. So we can think in those things. Those things are not well defined. So we say that everything which is part of the object, it should be well defined. So mathematically, and there could be more as well, part of the object. That's why we use the word object, not the thing. Because when we say thing, anything, it could be confusing. Okay. Now, one more question. For example, I say that there is a set S which has nothing in it. Do you think this set is empty? When we say an empty set, that's the way we write it. Okay? And another way to say this set is this notation. Phi. Some call it phi. It means that this is empty. Okay. Let me make your life easy. A set which has empty set in it. Do you think set S is empty? Let me think. No, no, yes, no, no, yes, yes, no, 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 yes. It's not empty because it has empty set in it. Okay. So you can get some idea that when we define set, it's not just, you cannot just take that. But most of the time, we'll not be talking about these kind of objects. But we will make sure that this set, what we are making, everything is distinct and well defined. So there is no confusion in the set. Now we go back to, since we now got the set, and we know what a set is, we look for the Cartesian product now. And we see that the Cartesian product is the product of two sets where everything is distinct and well defined. And when you multiply two sets, actually you get an order pair, which is AB. What does this mean? Okay, let's just change the color. Assume that we have a set A, which has 1, 2, 3, and we have a set B. Assume that it has A and B. And we want to know that what is A cross B. So the A cross B, it says that whenever you find the Cartesian product between A and B, you make sure that the first element, it comes from the set A, and the second one, it comes from the set B. So we could have one option, which is 1A, 1B. Can you guess? 2A, 2B. What comes next? 3A, yes. And then we have 3B. Can we make more of these? This is called the Cartesian product of two sets. And you can imagine that since each element in this set is an order pair, when you switch the order, things are not same. So 1A and A1, they are not same. So you can imagine that if you say B cross A, that's going to be different. That's not going to be the same. Okay, so this is the Cartesian product. Now it says that any subset of this Cartesian product is called a relation. Now we are going backwards. Got the basis. We are moving backward, trying to understand the concept. So for example, I say that, well, I have a relation R, which is equal to 1A and 1B. And there is another relation let's call this one as, let's call this one, let's call it T, which is 1A and 2A. Can we say that R and T, they are relations? The only condition what we have to see is every element of the set R is from A cross B? Is that true? So it means this is a subset of A cross B. What about T? Set T, every element of the set T, is it coming from A cross B? So we say that, well, this is also a relation. So we can make too many relations of one element or two elements or three or four, and a combination of them. Now we got some idea about the relation. The question is that how do we know that these relations are function or not? So let's just draw a kind of a visual idea. And this is your relation R. This is your set X. Let's call it A, since we already have mentioned. So this is your set A into set B. And here we see that we have two elements here. One, actually there's just one, and then we have A and B here. And we see that one is related to A and one is related to B. And the second one is T. So once again, we draw two circles and the relation T from A to B. And now we have 1 and 2. And here we have only one element, A. So we say that 1 is related to A and 2 is related to A as well. So we have two relations. Now the question is, let's go back to our definition, the function. So we learned that a function is a relation. So it means that a relation is become, it does become a function if a condition is fulfilled. So let's go back. What was the condition for a function? A function is a relation from a set X into a set Y such that every X in X has exactly one Y in Y. Every X, so you have to note every and exactly. These are the two words you should emphasize. Now I want you guys to have a look on these two and see which one you think is a function. I'm going to ask one by one. You have 10 seconds to think that which one satisfies the definition of function, that every X in X has exactly one Y in Y. Or you can say here, in this case, every X in A has exactly one Y in B. Or you can say both are not functions, or you can say all of them are functions, both are functions, or you can say one of them is a function. Okay? You can choose any answer. What do you think? T is a function? R is a function? Oh, none of them is a function? Neither. Both of them? T is a function? T. R. T. 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 Okay. R is not a function. Why is that? Because one input has two outputs. That's not allowed. You know, you go out for fishing and you put one bait on the fishing rod, you throw in the water, and you get 20 fish with one bait. Do you think it could be a function? Okay, one bait cannot have 20. Or for example, if you have one box and you have to deliver it, can you deliver it to two houses? One box, two houses? No. Okay, so it's not going to be a function if you have one input and you have two outputs. Okay, but if you have two boxes, they could be delivered in one house. That's okay. Okay. Why we do that? That's a good question. You see everything what we are trying to do in the range. So I want you guys to have a look here. Okay, I don't have good drawing, but I'm just trying to do something. So at least you will get some idea. What is that? Okay, or maybe there is something here. Anybody would like to sit here? It's a kind of, I would say that it's my imagination, and there is a walkway here. There is something wrong with this picture, technically. Can you guess? Anybody who really like to do some photography? Yes, good job. Say loudly to everybody.
It's your photos half and half and not split into photos.
Yes. So technically, if anybody see this picture, they are going to say that, well, this photographer, whatever is, has divided the whole picture into two equal parts. It's undecided that the landscape, the mountains are pretty or the water is pretty. So usually we say that it should be 1/3. There is a rule of 1/3. You divide it into 3 sects, and 2 you put one which you really loved, and one like which you think that this is secondary. When we do some experiment, for example, I say that, okay, I'm going to toss a coin. We don't say that we are expecting both heads and the tail. We are expecting one of them. Okay. So similarly, when we say that, well, what will be the output of this input? We are expecting only one answer. We don't like two answers. So, because eventually we are going to draw. So if this was your x-axis and this was your y-axis, and I say that, well, there is a point here, and I want to know that when I plug in this point, what I'm going to get. So if the answer is, well, we are getting two answers, we don't like it. You see, one x value, it has two y values. So we have a test which is called a vertical line test. If a vertical line hit the graph more than once, that's not a function. Let's write it down. It's vertical line test. It says that if it is possible for a vertical line to cross a graph more than once, then the graph is not the graph of a function. So now you got some idea why the definition of function is so important. Okay? So if we see, for example, there is another function which is like that, and we have x-axis, we have y-axis. So we see that every x value, it has exactly one y value. So we are fine with that. Or sometimes we have some function, we have x-axis and y-axis. So when the symmetries happen, okay, so there is a chance maybe two x values, they have exactly same height. And we are fine with that as well. Okay, so we call this one as a function as well. If anybody have any question about function, relation, all set. Okay, we are going to move slowly in the start and then gradually. When you got the understanding, we'll just move forward. Okay? Okay, the next definition is the domain. In general, we say that this set is the domain. Or for example, if you want to know that what is the domain of R, so we say that this is 1. What is the domain of T? Is 1 and 2. So in general, we are talking about the x values as the domain. In the range means the y values. Okay? But in general, we are saying that those x values which you can plug in and you get a nice output. What does this mean? It means that I have a function, assume that f of x, which is like 2 times x. Can you find any input value? This place is for the input value. and this is your output. So if you plug in x equal to 1, what do you get? 2. If you plug in x equal to 2, 4. Plug in x equal to 0, 0. So you get some idea. The question is that, can you find any value, any real number you plug in, and you don't get an answer? Can you find any? Think of any number you plug in, and I'm talking about the real numbers. You plug in, and the answer is undefined. And keep in mind, infinity is not a number. Okay, so we will not talk about that. So we see that, well, any number we can plug in. So we'll say that its domain is all real numbers. Okay. Assume that we have another function g of x, which is equal to 2x plus 1 divided by, assume that this is x squared. And now we see that we can plug in all the numbers except 0. Because when we plug in g of 0, this is going to be 2 times 0 plus 1 divided by 0 squared, which is 1 divided by 0. And it blows up. Okay. If you want to see the graph of this function, let's see if we have, this is 2x plus 1 over x squared. Y is equal to 2x plus 1 divided by x squared. You see what happened at 0? It's broken into 2 pieces. And you keep on going up. Okay, it does not matter where you go. And whenever you open it, you see, still there is nothing over there. So the function is blown up. There is no value as an output. So we say that, well, okay, this function has problem with 0, so we'll say that its domain is all real numbers except 0. Or you can say that from negative infinity to 0, union from 0 to infinity. That's another way to say the same thing. Okay, so domain is not all the x values. These are those x values when you plug in and you get a nice output. And when I say a nice output, it means a number in general. So if you are getting a real number as an output, then we accept that input as the domain. Another example could be, and I will conclude with that, assume that we have h of x is equal to x minus 2 squared root. Now we see that the square root, it has problem with the negative numbers because it become complex. But we are seeking only the real numbers. So this x minus 2, it has to be positive always to deal with the square roots. It means that this will be positive only when x is greater than or equal to 2. If it is less than 2, we see that the input of the square root is going to be negative. It's not going to be real anymore. So we'll say that for this one, the domain is equal to all real numbers such that x is greater than or equal to 2. If you plug in x equal to 3, it works. 4, it works. 3.5, it works. All the real numbers which are greater than or equal to 2 is going to work. Even if it is 2, square root don't have a problem with the 0. Square root of 0 is 0. Okay? Well, this is the end of this section. And I will see you guys next time. Have a good one.